Alright everybody, let's take a look at an ester reaction. Particularly this one we're going to look at a hydrolysis for an ester. So our ester that we're given here is ethyl heptanoate. That tells us a lot. Remember, the first name is always the alcohol and the second name would be what we need to know for the organic acid. So here we know this would be ethanol and heptanoic acid, and then there's other stuff here. Just some added information which is not needed but is always neat to read. So I've looked this up. I didn't have this one memorized. I just looked it up, thought it was kind of interesting. You'll find these type of compounds in like human sweat, which I thought was kind of cool when I was reading that. And then you also, certain wines and brandies, this will help give a certain distinct odor to them. And no, it doesn't make them smell sweaty. What you need to recognize is that sweat does not always have a stinky or smell to it. It just depends on the person's body chemistry. Different odors can have different levels of, for lack of better words, stink. But that's for another lesson. So anyway, so now this one right here, we're going to write a hydrolysis mechanism for the compound. So the way we normally think about this is we think of the alcohol, right? And then we think of the acid being added together and making this compound. So we can do that, but what we have to remember is hydrolysis, right? This process here is where it is breaking down. So it's the same as thinking of it as breaking apart into its components. So I think the best way to approach something like this is you take what you know. Okay, you take what you know. And what you want to do is break it apart. So right here, ethyl, so we know this is the ethanol, and heptanoate, so we know that that would be plus our heptanoic acid, right? That's what would have occurred. We know we're going to have a reaction, right? And then of course we would have had the ethyl heptanoate. Now we know that what I just wrote, this is the condensation reaction. So since hydrolysis is the reverse of that, then for hydrolysis, this becomes on our reactant side, and then this has to be our product side. So now remember, when these two form also, we're going to get some water that is formed. I always forget that. So that means what we have to have is ethyl heptanoate plus water and there we go. And then of course this would break down to make our ethanol or ethyl alcohol, either way, plus the heptanoic acid. Okay, so this right here, this is the hydrolysis. Okay, this is the hydrolysis reaction. So this part right here, that's not what we want. This right here was just us thinking about it. What we already know, what has to be added together. This right here is what we're going to want to show. All right. So what might be helpful is since we're used to writing these by themselves and then figuring out how to put them together, one approach is you could write the molecule here for ethanol, write the molecule here for heptanoic acid, so you can visualize that, and then build this, and then put them together. Another way to do that is, since we know that this part here, ethyl, that means 2, correct? And heptanoate, we know that means the 7, right? So we know this is an ester, so what we could do is just build the ester starting from the linkage itself. We know we would have to have carbon, double bonded to oxygen, and there's our single bonded oxygen. So here's our ester. This is what's linking this 2-carbon molecule, and here's the 7 part. So we come over here, and all we're going to do is add in the other 2 carbons that we know that we have. So here's the ethyl part, right? And then heptanoate. So there's 1, 2, 3, 4, 5, 6, 7. And so we know that there's hydrogen all the way around this hydrocarbon chain, right? Plus our water. And so again, this is for training purposes. You know, I don't write the hydrogens in there, but you would have to make sure you write that. And then of course, got a reaction, our equilibrium. And so notice, you'll notice that I'm always drawing a half arrow. So when the reaction is driven in this direction and this direction, if you were to think of both of these together, if you were to bring it down, what it kind of symbolizes is 2 halves of the arrow. So it's going in this direction and that direction. This is a typical way to draw that. All right. So then we have ethanol. So that's 2, 1, 2. All right, because the eth part, remember methane, ethane. So then we have the hydroxyl part to it, plus there's 7. So that's 1, 2, 3, 4, 5, 6, 7. And then it's the heptanoic acid, so we need our carboxylic acid group. Now I'm just going to add in my hydrogens. Okay. And there's the hydrolysis reaction. So now if we think about this, remember we always have a catalyst. And so when we're up here, I mean, I guess I shouldn't have scribbled through that, but you can still see this right here. So ethanol plus heptanoic acid. So if you think about it, we've always written the hydrogen ions, and then there was some heat to help drive the reaction, right? So in lab, what you see is that, so if we think about this, if we add heat, that means as these 2 things heat up, so the temperature increases and this forms. Well, if all of a sudden we decrease the heat, if there's a decrease in heat, then it would go back to the parts that we had. So now let's take a look at this. These 2 things, when heated up, make this. So these 2 things, if heat goes back in this direction, so the heat we're going to want to put down here. Because these 2 things right here, if they're catalyzed with heat, would then form this ester reaction. That would be the condensation part, right? And so then of course we know that we've got some hydrogen ions that would also have to be added to that, right? So what we know we have here is a decrease in heat. So when the heat decreases, it goes in this direction. So where we're writing the arrow kind of makes a difference. And there's multiple ways to write this. Sometimes you'll see symbols like showing that there's a decrease in heat, so a delta change. So you could write a decrease in delta. But we're just going to write this. We'll be consistent. I'm not gonna mix up too much for you. So notice we're just following the same practice here. If we have to reverse it, it makes sense that these 2 together with the hydrogen ions and the heat go into there, making our ester, right? So now there's the first part, write the hydrolysis reaction for it. Check, that's done. Now let's write a balanced chemical equation for it. So if we think about this, we know in a previous lesson how we've talked about how we put this in the middle, COO, we put that in the middle, right? And then the typical way to write this is then this part right here goes in the front, and then this part here goes in the back, right? So we've got 1, 2, 3, 4, 5, 6, right? So that is C6, H2, 4, 6, 8, 10, 12. That one on the end, that would be H13. Correct? Then we've got C2, 2, 4, and 1 is 5, H5, and then we also have our plus H2O, correct? And then, of course, we have our catalyst that we need to write. And then if we look here, we remember this is the R part, so that's C2, H2, 4, 1 is 5, H5, and then we have OH at the end. And then right here, remember we write this, for these we're going to put COOH at the end, COOH. So that's 1, 2, 3, 4, 5, 6 carbons right there. 6 carbons, 2, 4, 6, 8, 10, 12. There's 13 hydrogens right there, and then we have COOH. COOH. And there's our reaction. That was pretty easy. Alright, so we've got that part done there. Check. Now we just need to calculate the formula and molar mass weights. So we've done that in the previous screen. Now that we have that, what helps with this is if we take this and we just think of the empirical formula for this. So we've got 6 plus 1 is 7 plus those 2, so that's C9. And then our hydrogens, we've got 13, and then there's 5, 13 and 5, so that's 18. And then we have 2 oxygen. So this, remember, is our empirical formula for this formula for our ester compound, right? Let's look back up at the problem. We want to calculate the formula in molar, for the products, okay? So I just did this. We won't need this, but that was good practice, right? So we just practiced that this was our empirical formula. And empirical formula of the ester. But the problem is asking for the formula and molar mass for the products. So what we need to do actually is calculate this. So let's go with the formula mass. Alright. Formula mass. So we've got, let's see here, we've got our ethanol, so we've got the C2H5OH, so we've got carbon, we have hydrogen, and we have oxygen. And so carbon, we see here we have 2 of those. Hydrogen, we've got 5 and 1, there's 6, and 1 of those. So remember, this is 12.01 AMU. Hydrogen is 1.01 AMUs. Remember, atomic mass units. And then oxygen, remember, we're rounding that up to 16. We'll just do some basic math here. Alright, so this would give us 24.02 AMU. This would give us what, 6.06 AMU, and then of course this is 1 times 16. If we add all this up together, let's grab our calculator. So let's say 24.02 plus 6.06 plus 16. You should get 46.08. All right. 46.08 AMU. So there's the molar mass for the ethanol, right? So we know that molar mass molar mass for ethanol would be 46.08 grams of the ethanol for every 1 mole of the ethanol. Alright, so we've got molar mass done for this compound. So now we just need to do this one, C6H13COOH. So this would be our heptanoic acid. Alright, so we had C6H13COOH. Okay. Alright. So let's just list everything out again. So we got carbon, hydrogen, and oxygen. Carbons we have what? 6 and 1, there's 7. 13 hydrogens, 1 plus 1, so that there's 14. And then oxygens we have 2. Okay. Again, 12.01 for the carbon. And at this point, this is, you should see that this is just pretty monotonous. It's just the same calculations over and over again. The only thing that changes are the numbers. So 7 times 12.01, you should get 84.07. Alright, make sure you are doing these calculations with me. 14.14 AMU, correct? Wow, that's pretty bad. Let me erase that for you. I'm going to try to be at least a little neater. So that would be 14.14 AMU. And then, let's see here, right here, what we got? 2 times 16, that'll give us another 32 atomic mass units. So 84.07 plus 14.14 plus 32, you should get 130.21 AMU. Alright, so now we want the molar mass for this particular product as well, which means that in 1 mole of it, an Avogadro's number of molecules of this, we'd have 130.21 grams of heptanoic acid for every per 1 mole of heptanoic acid. So the only thing that changes every time is the formula. So it's always X number of grams per 1 mole of whatever it is you're looking at. Okay. So if I'm correct, we have done everything we're supposed to. We wrote the hydrolysis reaction, check. We wrote the balanced equation for the reaction, check. We calculated the formula mass, check. Everything's good. Alright, hope this helped, and keep in mind you also need to be able to do the line structures for these as well. So see if you have any questions on that, but remember every point it will be a carbon atom. Hope this helped, and we'll talk soon. Bye.